So Edward, it's a great pleasure to, in some sense, give you the last word in this. And
I don't think I merit it, but
and because no, you're eminently qualified, being both responsible for many of the wonderful, partly responsible for many of the wonderful things were highlighted today. But perhaps to start the discussion, talking about the gap or the gulf
Yes.
between physics and mathematics.
Yes.
We heard wonderful examples how the fields are overlapping and interacting.
yes.
How would you assess the state of this gap, and if anything, what are the major obstacles?
Well, the first thing I'd like to remark is that to the extent that a gap developed in the 20th century between physics and math, it wasn't because of personalities, bad judgments, somebody had too much influence. It really was inherent in the logic of the two subjects. So mathematics, by the early 20th century, was developing abstract theories that were extremely interesting and successful, not necessarily so close to whatever roots mathematics might have in the physical sciences. You might say that mathematics was transcending its origins by the early 20th century. Physics, on the other hand, especially after the development of quantum mechanics, went in directions that were much harder for mathematicians to appreciate. Two of our speakers this afternoon, both Karen and Tom, drew attention to the fact that it's actually extremely difficult for mathematicians to understand quantum field theory.
Yes.
And that's been an enduring mystery. But since quantum field theory has been increasingly central in physics since the late 1920s, that created, just in the logic of the subjects, a gulf between them. And that was enhanced after World War II. In the quarter century after World War II, there was an incredible flood of discoveries in fundamental physics, so that the progress of physics was largely driven by experiment in a way that might not have made the subject seem too enticing to mathematicians, especially given that the mathematical foundations were so murky. So that would be kind of a summary of where the world was when I was a student, for example. When I was a student, a physics graduate student would not be exposed, I was not, and I think others would not be either, to any ideas at all in contemporary mathematics, or really even in 20th century mathematics practically. Now, clearly things have changed a lot since then, and one of the biggest reasons that things have changed is that when the standard model of particle physics developed, first of all, theory kind of caught up with experiment in a way in physics. So what theoretical physicists were doing after that was a bit different. Can you hear, by the way? Is my microphone?
Yes, it's working. Yeah.
Okay. So, okay. Theory in a way had caught up with experiments, but when the standard model was in place, it led physicists to ask new kinds of questions that weren't possible before without the standard model. And it made what physicists could potentially do more interesting mathematically. And there were visionaries like Michael Atiyah, who Greg mentioned before, Robbert and others, Isinger, who had a vision that this interaction could be important. So definitely the story has changed in the period since I was a graduate student. And string theory has also been an important part of that change. I'd like to remark, though, that although there's been a huge change since I was a student, we shouldn't exaggerate. There's also still a big separation, almost inescapable separation, between the goals and nature of the two subjects. So, well, physicists usually are not much interested in the details of mathematical proofs, which means that usually even physicists in whose work modern mathematical ideas are important might not really understand deeply the ideas that they're working with. And on the other hand, since the difficulty for mathematicians to understand quantum field theory has endured, it makes it extremely difficult for mathematicians to understand what physicists are really trying to do.
One thing I find kind of interesting that somehow crucial in that connection are quantum field theories.
Yes.
And although it's a well-defined mathematical challenge,
Yes.
it's even one of the millennial problems to rigorously construct, essentially,
Yes.
a modern gauge theory. that's not, you might think that's where all the attention on both sides is directed, but in some sense there are very few people trying to build that mathematical structure, right?
Yes, I think that's unfortunate, but unfortunately, to show that four-dimensional gauge theory exists as a well-defined mathematical structure, it's not something one person could do. It would have to be a whole school of people really determined to tackle that problem. And to make it happen, there'd have to be a lot of interest in the math or physics worlds, at least once, ideally both, but at least one, on the intermediate steps. You wouldn't get to the end all at once. And so the intermediate results would have to be considered exciting.
So you also pointed out that the crucial concepts in physics
Yes.
lack a certain kind of mathematical rigor, perhaps almost by nature.
Well,
Do you
I don't know
feel
by nature, but by our present understanding, certainly.
lack of understanding, perhaps?
Maybe,
yes.
I don't know.
You feel that there is genuine interest in the mathematical world to understand these concepts?
Well, my experience is that, in general, there's a lot of interest among mathematicians in whatever physics they can understand.
Mm-hmm.
But unfortunately, quantum field theory is difficult to understand. So, as I remarked already, two of our speakers today drew attention to that.
Do you actually feel that physicists could learn from perhaps a different mathematical point of view on quantum field theory? Because honestly, I think in the physics world we also are struggling in some sense to have a clear understanding what these crucial objects are. We have many different perspectives, but not a unified perspective.
You could, I really don't have the slightest idea, Robert.
Mm-hmm.
I'd be happy to hear your guess, to be honest. Do you think there's an alternative formulation of quantum field theory that would make its mathematical foundations more obvious?
Well, I would be willing to bet that whatever formulations of quantum field theory we have now
Yes.
are preliminary, because there's such bizarre correspondences. I really feel that in some sense our understanding is more a set of maps as you find in an atlas instead of a nice globe that has kind of a definition that mathematicians would appreciate.
Maybe.
I mean, one thing and I won't do because I will make you very uncomfortable to try to predict the future. But we had a preliminary conversation. I found it interesting. We were talking about, suppose you would go back
Yes.
30 years in
Yes.
time, and I would have asked you, a 30 years younger self, what you might think would be the most promising direction in this interface of math and physics. What would you have said, and what did somehow reality tell us?
Well, I was thinking more of what I might have said 30 years ago about where there might be exciting progress in understanding physics better,
Mm-hmm.
and whatever I would have said would have been completely wrong. So,
Perhaps you should explain this to us. Yeah.
one thing I certainly would have been obsessed with 30 years ago was understanding at a more fundamental level what string theory was coming from, what it actually meant. And I would have envisaged two somewhat different questions. One is, what's a fundamental formulation? What are the basic laws? And the second is how the system behaves. So let's just remember that usually in physics it's sort of a two-step problem. What are the laws and what are the solutions of the equations? Usually what are the laws comes first and then you try to solve them. To give an illustration where there's a very wide gap, but which is featured in some lectures this afternoon, the theory of the strong force, or the nuclear force, which Greg Moore told us about, for example, also which Nima and Tom were talking about in the last session. So the equations were formulated more than 40 years ago. It's still very limited, our ability to solve them today. So anyway, I would have focused 30 years ago on trying to understand what the symmetry principles, the fields, the equations were, and assumed that solving them and understanding the strong coupling behavior was for the second stage. But oddly, the progress was made in the opposite direction.
Because it's more the second question that we have answered, right? We have many more solutions.
Okay, sorry. I'm afraid I haven't managed to give a sensible explanation to those of you who aren't string theorists of what I'm talking about. And I don't think I'm going to be able to fix it either. But things happened in a completely backwards way, where there was a lot of progress in understanding what happens when quantum effects are big, what happens for strong coupling, even though there's been very little progress in understanding the fundamental equations.
So in some sense we were misguided perhaps in the success of Yang-Mills theories and...
Well, the analogy with traditional physical theories didn't unfold in the way that I would have assumed.
I would argue that perhaps one of the most mystifying concepts that's now very much alive in our theories of quantum gravity, but it's kind of mystifying for a mathematical point of view, is the kind of emergence of space-time. Because it's somehow almost undercutting the natural role of geometry in spaces.
Yes.
What are your view on that? Is that something that we...
Well, you tell me yours first.
Well, I think in some sense, you know, we are lacking the mathematical language to describe these, this. So I see this as, you know, there's this kind of major conflict between geometry and space on one side and algebra and quantum theory on the other. And I think many of us always had geometry in the back of our minds as kind of more fundamental. And this might, you know, we have to find structures where geometry is somehow much more an afterthought and not the initial starting point. And I think that's, we have some toy models, but we don't have an overarching idea, I think.
So, of course, one thing that did happen in the last 30 years, starting with Maldaceno's holographic duality discovered in 1997. So we did find a non-perturbative formulation of a world with quantum gravity, at least in a certain type of situation. It had little in common with anything we would have been imagining had we had this discussion 30 years ago. It was an example of emergent spacetime. And since it's the only way we know how to make that happen, it colors a lot our thinking to the extent we have any concrete thinking. So, but I tend to think that we would still be wrong.
Still be wrong?
Yes.
So looking back in time, since you, you went, there were many high points of beautiful math, playing a crucial role in physics and physics ideas. For you personally, what were some of the most satisfying results?
Well, the story Greg told us about, where it turned out that the connection of Donaldson theory with Yang-Mills gauge theory was actually, with quantum Yang-Mills gauge theory was actually useful. That was a lot of fun. That was a kind of spin-off of my work with Natty Seiberg on dynamics of n equals 2 super Yang-Mills. But there have been a lot of other fun episodes.
Mention one other.
Well, one I'll mention because it was a surprise because it wasn't at all clear why it was correct, was the relation between matrix models of two-dimensional gravity and intersection theory on the moduli space of Riemann surfaces. So that was a surprise, well, because there was no good reason to think it was true, really.
But it was not a wild guess, was it?
It was a semi-wild guess. I mean, yeah, it was a reasonably wild guess.
I remember...
I'm not going to contradict anyone who says it was a wild guess.
This was actually 30 years ago, and I was telling Edward that actually the first day I arrived here in Princeton, you shared that wild guess. So I think, what's happening here? You know, this is, so another thing, which I find remarkable, if think about these interactions, is not only that there is interaction between physics and math, but also there's sometimes physics brings connections between different fields of mathematics, right? Which are quite surprising. You mentioned this example of intersection theory on the moduli space of Riemann surface, integral hierarchies. These are fields which, in the mathematical world, almost belong to different countries that are. So, you have any observations? Why physics is able to do this?
I guess the universe was created by a mathematician.
Perhaps I'm forcing you in a certain direction, but do you feel that's perhaps, though, mathematics is more unified than mathematicians are, that we kind
Well,
of divide our subjects perhaps a little bit too over-eagerly?
Well, let me take a slight digression from not take the question literally and share the following thought though. I think that the reason that a lot of interesting mathematical ideas have come from physics has nothing to do with how talented physicists are as mathematicians. It's purely that the physical theories we're trying to grope for contain a lot of mathematical secrets. But these physical theories are still very little understood as of 2019. So I think we've seen only a tiny fraction of the picture.
And actually, relating to that, there is this kind of a folk theorem in physics. We talked about this from Steve Shanker, who says that there's one subject in mathematics you always avoid, and that
Yes.
turned out to be the
Yes.
relevant one for your next paper,
Yes.
right?
Yes.
Is there any subject in math you are consciously avoiding?
Well, I've judged that some things are too abstract for me to try to learn them.
Too abstract.
Yes.
And is there part of you that worries that actually they might be relevant still?
Well, I'm more worried about not being able to understand properly the things that aren't too abstract. And that But I think I would go out slightly out on a limb and say that I decided quite some years ago that in my career, a really satisfying interaction of physics with number theory would probably not happen.
Not happen in
No.
your career?
That's actually why I focused on geometric Langlands, not real Langlands. Because, well, and I actually think that the reason I was able to achieve something was that I
You refrained from that
decided
urge
to not be more ambitious.
Yeah. But do you feel that as a large part of math that is, to first approximation, still not connected to physics?
Well, I am a little bit jealous of our successors in future generations who maybe will discover a structural relationship between physics and number theory. But I've accepted that I'm presumably not part of that generation. Although if I live to Freeman's age, maybe I've got a shot.
As we've been talking about relation between math and physics, we also briefly want to talk about another gap, which is perhaps between theoretical
Yes.
physics and
Yes.
experiments in the
Yes.
world. Now it's getting late, and we will be close to finishing. So at this point, I can ask anything, I feel. But what's your view on all of that huge structure we've been building in theoretical physics? How confident are you that this is connected to the real world? And you have made in the past remarks that particularly string theory is something that somehow almost came too early, right? We have these very powerful ideas. We only are scratching the surface in terms of what their content is. How confident are you that we are describing at least part of our reality?
I'm actually personally reasonably confident that what we're doing is a lasting contribution. But I'm less confident that we'll really be able to put it on a completely solid footing. It depends upon being lucky with experiment, I would say. So we've been able to get experimental clues that come from way beyond the energies we can usually reach where we're lucky. For example, with neutrino masses, cosmic microwave fluctuations. Maybe we'll see the B mode, maybe we'll discover proton decay. Maybe we'll see accelerator physics beyond the standard model and it will give us clues. But none of those things come with guarantees,
Right.
as indeed life usually doesn't.
And what about some of the theoretical successes? So for instance, the fact that we now have working theories of quantum gravity, does that somehow add to your conviction that we are on the right way connecting to reality?
I think so, yes. I think so understanding how quantum field theory can work with gravity enriches our understanding. And understanding that quantum gravity is an inevitable part of quantum field theory, though it's a more difficult point to explain to those of you who aren't physicists late in the afternoon, but it follows from the Model-Sena duality. That also enriches our understanding.
Well, often I hear questions about whether is string theory wrong or right, but I often answer there's no way in which we ever will get rid of string theory, right? Because in some sense it's an integral part of
Yes.
the theories that we already are using to describe parts of nature.
Yes, that's true, but not completely satisfying. Let's not give up on the dream of finding the vacuum that describes the real world.
I think once you said something that if string theory is not right, you were wondering who are living in the universe described by string theory, because it's such a beautiful universe. You still feel a little bit like this?
Well, to me it's implausible that humans stumbled by accident on such an incredible structure that sheds so much light actually on established physical theories and also on so many different branches of mathematics. And that's all an accident and has nothing to do with the real world. So I personally would consider that implausible. So the honest answer is that personally, as I told you before, I have confidence that the general enterprise is on the right track. But I don't claim that the argument I've given is scientifically convincing.
Well, I think it actually is a wonderful note to end today's wonderful meeting. I think my role is here to finish this evening, and I do this by inviting you all to thank all speakers, and particularly congratulate Graham on his book. And if those of you are interested in it, I think you can get signed copies. You will sign outside Wolfenson Hall. So thank you all very much for being here with us.